Here are two people. The first sets aside $200 a month starting now. The second does exactly the same but begins 10 years later. Same monthly amount, same returns. 40 years from the start, here is where they each land. The early starter put in only $24,000 more over those years. And yet, they finish with about $281,000 more. How can a 10-year head start turn an extra $24,000 into an extra $281,000? You may have seen this called the eighth wonder of the world, a line often attributed to Albert Einstein. There is no reliable evidence he ever said it, but the true answer is mathematical and far more beautiful than any quote. So let us build that answer from the ground up, starting from a single dollar of interest. And along the way, we will meet a remarkable number hiding inside all of it. Let's start as simply as possible, $1,000, earning 10% a year. It turns out there are two completely different ways that interest can work, and the difference between them is the whole story. The first way is called simple interest. Every year you earn 10% of your original $1,000. That's $100, the same $100, every single year. The second way is compound interest. Here, each year, you earn 10% of whatever you have right now, and that includes all the interest you have already collected. Last year's interest becomes this year's principal. Watch what that small change does year by year. After the first year, both accounts hold $1,100. They are exactly the same. But in the second year, compound interest takes 10% of $1,100 and edges $10 ahead. Where did that extra $10 come from? It is the interest earned on the first year's interest, and it keeps happening. Each year the lead grows because the interest itself is now earning interest. In fact, the entire gap between these two columns is nothing but interest that interest has earned. Look at the structure underneath the numbers. Simple interest adds the same $100 each step. That is an arithmetic sequence. Compound interest multiplies by 1.1 each step. That is a geometric sequence. One of them grows by addition, the other grows by multiplication. And over time, multiplication wins, not by a little, but by an enormous margin. Stretch the same $1,000 over 40 years. Simple interest rises in a perfectly straight line, reaching $5,000. Compound interest bends upward and finishes above $45,000. The shaded region between them is all interest earning interest, and it has grown to dwarf everything else. That single idea, interest earning interest, is the entire engine of compounding, which leads to a natural question. If compounding once a year does this, what happens if we compound more often? Every month, every day, every instant? Last time we compounded once a year. But why stop there? Suppose we split the year into equal periods. In each one, you earn a fraction of the rate, r divided by n. Over t years, that is n times t separate compounding steps. So our formula becomes p times 1 plus r over n raised to the power n times t. Let's put it to work. $3,000 at 5% for 5 years. Compounded once a year, it grows to $3,828. Twice a year? A little more. 4 times a year? More still. Monthly, daily. Each time we compound more often, the final amount grows. But look closely. Every jump is smaller than the one before it. $11, then 6, then 4, then 2. The gains are shrinking. The values are not running off to infinity. They are piling up against a ceiling. Even compounding every single day gets you to within 7 cents of it, and no amount of extra compounding will ever break through. This ceiling is what we call continuous compounding. Interest added not yearly, not daily, but at every instant. And the exact height of that ceiling is set by one of the most important numbers in all of mathematics. To uncover it, let's strip this problem down to its simplest possible form. From the last section, the purest version of compounding is this: $1 at 100% for 1 year. The final amount is 1 plus 1 over n, all raised to the power n. Watch the sequence as n grows. 1 period doubles your money to $2. 2 periods give 2 1/4. 4 periods, about 2.44. 12, about 2.61. 365, about 2.71. The values keep climbing, but more and more slowly. So here is the real question. Does this sequence settle on a single number or grow without end? One powerful fact decides it. If a sequence always increases and never rises above some fixed ceiling, then it must converge. So we only need to prove two things, that our sequence always increases and that it stays bounded. Begin with the binomial theorem. Expanding 1 plus 1 over n to the power n gives a sum of n plus 1 terms. Written out, each term is 1 over k factorial, times factors like 1 minus 1 over n and 1 minus 2 over n. Now make n larger. Each of those factors, like 1 minus 1 over n, climbs closer to 1. So every term grows, and a larger n adds even more terms. The sequence can only increase. One half of the proof is done. For the other half, notice each of those factors is less than 1. So every term is at most 1 over k factorial. That makes our value no larger than 1 plus 1 plus 1 half plus 1 sixth plus 1 24th, and onward. Now the key step. 1 over k factorial is never more than 1 over 2 to the k minus 1. Those halves form a geometric series summing to exactly 2. So the whole thing is at most 1 plus 2, which is 3. The sequence never reaches 3, always rising forever below 3. By our principle, it must converge to a limit. And that limit is a very particular number, 2.71828, continuing forever. A number which, as we are about to see, has more than earned a name of its own. That number is one of the most celebrated constants in all of mathematics. We call it Euler's number, after Leonhard Euler. To 15 decimal places, it is 2.718281828459045. And E wears two faces. The first is the one we just uncovered, the limit of 1 plus 1 over n, raised to the power n, as n runs to infinity. This is the face of compounding. The second is an infinite sum. 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial forever. That is 1 plus 1 plus 1 half plus 1 sixth plus 1 24th and on. They look nothing alike, yet they define the exact same number. But they are not equally useful. The limit crawls. Its error shrinks only as fast as 1 over n, so you would need around 1,000,000 periods just for 6-digit accuracy. The series sprints. Because factorials grow explosively, each new term is minuscule, and after just 10 terms, you already have a correct to 6 decimal places. This is how E is really computed, and E is no ordinary number. It is irrational. Euler proved in 1737 that it can never equal one whole number divided by another, so its digits run on forever with no repeating block. It goes further still. E is transcendental, shown by Hermite in 1873. It is not the root of any polynomial with whole number coefficients, although its opening digits hide a charming coincidence. 2.7, then 1828, 1828, then 45, 90, 45. A lovely way to memorize them, but a coincidence all the same. For now, E is just a number. Its real power is unleashed the instant we open the door to calculus, where E becomes the natural language of growth itself. In the last sections, E emerged from compounding at shorter and shorter intervals. Now let's ask what compounding at every instant truly means. Take a tiny slice of time, dt. Over that sliver, your balance A earns interest at rate R, so the gain is R times A times dt. That tiny change in A, divided by the tiny change in time, gives a differential equation. The rate of change of A equals R times A. Read it out loud. The speed at which your money grows is proportional to how much money you have. The more you hold, the faster it climbs. Geometrically, at every point on the growth curve, the steepness equals R times the height. Low balance, gentle slope, high balance, steep slope. To solve it, we separate the variables, gathering every A on one side and integrate both sides. The natural logarithm appears, and unwinding it gives the answer. A of t equals p times e to the rt. Continuous compounding in one clean formula. Let's check it. The derivative of pe to the rt is r times pe to the rt, which is exactly r times a. The formula satisfies our equation perfectly. And now the payoff. Remember the ceiling from a few sections ago? $3,000 at 5% for 5 years compounded continuously as 3,000 times e to the 0.25. That is $3,852.08, the exact ceiling we could not break. It was E all along. This is why E is called the natural base of growth. It turns the simplest law of growth into the cleanest possible formula. And hiding inside all of this is the single most remarkable property of E, the one that makes calculus fall in love with it. E to the x is its very own derivative. We ended last time with a teaser, and it is worth pausing on because it is the property that makes E special. The derivative of e to the x is again e to the x. Think about what that means. The derivative is the slope of the curve. So at every single point on this graph, the height of the curve and its steepness are the exact same number. At x equals 0, the height is 1, and the slope is 1. At x equals 1, the height is e, and the slope is also e. The function literally grows at the rate of its own value. Why should this be true? The cleanest way to see it is through the series. E to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. Now differentiate it term by term. The 1 vanishes, x becomes 1, x squared over 2 factorial becomes x, and in general x to the k over k factorial becomes x to the k minus 1 over k minus 1 factorial. Look closely. That is the very same series we started with. Differentiating it gives it right back. Now, every exponential has a derivative proportional to itself. In general, the derivative of b to the x is the natural log of b times b to the x. For base 2, that constant is about 0.69. For base 10, about 2.3. Every base drags along an awkward multiplier, except 1. For base e, the natural log of e is exactly 1, so the multiplier disappears. That is what makes e the natural choice, and it works in reverse, too. Take the natural logarithm of pe to the rt, and it untangles into ln p plus r times t. On a logarithmic scale, exponential growth straightens into a perfect line, and its slope is exactly the growth rate r. This is why we call it the natural logarithm. One elegant fact, that e is its own derivative, is what places it at the very heart of calculus. But you do not need calculus to feel its power. Next, we will turn all of this into a shortcut you can do in your head, the famous rule of 72. Here is a trick that feels like magic, yet falls straight out of the math we just built. To estimate how many years it takes your money to double, just divide 72 by the percentage growth rate. That is the entire rule. So where does it come from? Doubling means the final amount is twice the start. Using continuous growth, 2p equals p times e to the rt. So 2 equals e to the rt. Taking the natural logarithm, r times t equals the natural log of 2, which is about 0.693. Solve for the time, and the doubling time is roughly 69.3 divided by the percentage rate. That is exact for continuous compounding. You could call it the rule of 69.3. But nobody wants to divide by 69.3 in their head. So why do we use 72? First, real accounts usually compound once a year, not every instant. That nudges the true number up into the low 70s. Second, and this is the clever part, 72 is wonderfully divisible. It is 8 times 9. It splits evenly by 1, 2, 3, 4, 6, 8, 9, and 12, so the mental arithmetic is effortless. And how good is the estimate? Surprisingly good. At 6%, the rule is off by under 1%. At 10%, about 1%. At 12, still under 2, and right around 8%, it is nearly perfect, off by less than 0.1%, so take 8%. 72 divided by 8 is 9. Your money doubles in about 9 years. The exact answer is 9.01 years, from a calculation you can do in a single breath. Now, doubling every 9 years might sound slow, but watch what happens when you give that doubling enough time by starting early. We just saw that at 8%, money doubles roughly every 9 years. That sounds slow, but watch what happens when you let those doublings stack up. Start with a single dollar and simply wait. After 9 years, it doubles to $2. After 18, it has doubled again to $4. After 27 years, $8. After 36, $16. In round numbers, a single dollar becomes about 10 times itself in 30 years, with no extra effort at all. But here is the part almost everyone gets wrong. That growth is not spread evenly across the years. Look at the curve. It crawls along for the first decade or two, then erupts. In fact, more than half of the entire final amount is created in just the last 10 years, which leads to the single most important lesson in all of personal finance. Take the very same one-time deposit, let it grow for 40 years, and it becomes about 22 times itself. Start just 10 years later, with 30 years to grow, and it reaches only about 10 times. That 10-year head start more than doubles your final wealth from the identical dollar. Put bluntly, every decade you wait roughly cuts your final result in half. So why are the early years so unforgiving? Because of how doublings grow. Each doubling is larger than everything that came before it, combined. That last doubling alone, from 8 to 16, adds more dollars than the entire first 27 years produced. Starting early is how you buy yourself those final giant doublings. And this is not only about lump sums. The same law rewards steady saving. Set aside $200 a month at 8%. Over 40 years, it grows to roughly $698,000. Over 30 years, only about $298,000. That is more than double the result, from only a third more money paid in. Time, not the size of each deposit, is doing the heavy lifting. None of this is a modern invention. The struggle to understand money that grows on itself is one of the oldest stories in mathematics, stretching back 4,000 years. Everything we have built, the doublings, the limit, the number e, might feel modern. It is anything but. Travel back 4,000 years to Babylon. Clay tablets already record loans charging 20% on silver and a full third on grain. Their very word for interest, mash, literally meant offspring, money giving birth to more money. One tablet even asks how long it takes a sum to double. A rule of 72, 4,000 years before we derived it. Jump to 1494. Luca Pacioli, the father of modern accounting, prints a doubling time shortcut in his great arithmetic textbook. It is the rule of 72 in print more than 5 centuries ago, 1683. Jacob Bernoulli is studying interest compounded more and more often. He examines 1 plus 1 over n, raised to the n, and proves it settles between 2 and 3. It is the very first sighting of E discovered fittingly inside compound interest itself. Then comes Leonhard Euler. He gives the constant its name, E, and computes it to 18 decimal places, turning a curious limit into one of mathematics' great constants. And in 1790, Benjamin Franklin makes a bet on compounding that spans centuries. His will leaves £1,000 each to Boston and Philadelphia to be lent at 5% and left to grow. He predicted it would swell to £131,000 in a century. 200 years later, the funds were worth millions, bankrolling schools and museums. From Babylonian clay to a founding father's will, this is the same mathematics. And remarkably, that same equation reaches far beyond money into worlds you would never expect. We have followed compound interest from a single coin to the number E. But here is the twist that makes it truly universal. Strip away the dollars, and what remains is one idea. A quantity whose rate of change is proportional to its own size. That gives the equation dN/dt equals Kn, whose solution is n naught times e to the kt. When k is positive, things grow. When k is negative, they decay, and wherever this pattern appears, E appears with it. World 1, physics. A lump of radioactive material loses atoms at a rate proportional to how many remain. So its amount follows n naught e to the minus lambda t, the same curve as our savings, simply reflected. And its half-life, the time to lose half the atoms, equals the natural log of 2 over lambda. That is the exact mirror image of the rule of 72 for doubling money. Carbon-14, with its 57-30-year half-life, is how we date the ancient world. World 2, artificial intelligence. As a neural network learns, the size of each update, its learning rate, is often cooled down. One common choice decays it as eta naught e to the minus kt. The very same constant that grows your savings is what gently slows a model as it converges. World 3, finance, run in reverse. A dollar promised in the future is worth less today. To find its present value, you discount it by e to the minus rt, compound interest played backward. A dollar in 10 years at 5% is worth about 61 cents right now. This very term sits at the heart of the Scholes formula, the equation that prices the world's options markets. The e to the minus rt quietly discounts the strike price. Step back and look. Finance, physics, and artificial intelligence, 3 worlds that could not seem more different, all governed by a single differential equation, and a single constant, E. Which brings us, finally, to the one lesson that ties this entire story together. We started with a single coin and a simple question. What really happens when money earns interest on its interest? That one question carried us a remarkable distance. From simple versus compound growth to compounding ever more often, to pushing that idea all the way to its limit, where the number E emerged. We gave it a name, discovered it is its own derivative, and watched it surface in physics, finance, and artificial intelligence. So, what is the real lesson? There are two. The first is practical. Time is the real multiplier. Compound interest does not reward cleverness or timing, it rewards patience. The doublings stack on top of one another, and the largest one is always the last, which means the best moment to begin was always earlier than now. The second lesson is deeper. E is not some arbitrary number a mathematician picked. It is what must appear, inevitably, whenever a quantity grows in proportion to its own size, whether that is a bank balance swelling or a radioactive atom fading away. We began by retiring a quote that Einstein never actually said, so let us end with something truer. Compound interest may not be the eighth wonder of the world, but the number it gives birth to, just might be. Thank you for following this story all the way to its end. If it gave you a new way to see the number E, that is the real return on your time.